Good morning. I am Tejas Patel and my friend Nisar Patel. Today we are presenting the work on performance evaluation of network function virtualization. Next. Introduction to NVF. NVF virtualization network applications like firewalls and routers, eliminating the need of physical devices. It also enhances scalability, reduces cost, and increases flexibility. With NVF, you can scale services up and down easily, cut hardware costs, and deploy functions faster. And its use case are it is a real world example where NVF is applied in modern networks, like it is applied in routers, firewalls, and also in load balancers. Next. The need of performance of evaluation ensures NVF meets services legal level agreements. It means that SLAs define service quality, its performance is better, and it identifies bottleneck affecting latency, throughput, and reliability. Bottlenecks can slow things down. This step finds them. It is optimizing the resource allocation as it helps CPU to assigning memory efficiently to NVFs. It also evaluates the trade-offs between performance and cost. Next. Throughput. How a throughput means how fast data can move from one system to another. Its latency period means time a packet required to go from source to destination. Packet loss is the percentage of packets that lost during the transmission. That should always be low as it will become higher than the information that we want to transfer. It will not go effectively. The resource utilization is also low in NVF as there is not much need of CPU usage. Memory is required less and bandwidth is also used properly, and its scalability is very high as NVF handles increased traffic or users. Next. Factors that affects NVF are virtual machine because its containers are light and virtual machines uses more resources. Hypervisor efficiency. Hypervisor efficiency, it means that the KVM, ZDN, VMware differs in how fast they handles virtualization. Network input output bottleneck can limits the data flow also. Service change complex service changing complexity. It changing the changing many VNFs can cause delays. Hardware acceleration. This tool speeds up packet processing, and we will get the process data in much lesser time. Next. In performance evaluation technique, the benchmark tools are DK test suites. It is used to test packet processing speed. PKTGN, a packet generator for simulating traffic. Miminet, that creates virtual networks for testing, and it helps in seeing that the real packet will work how well. The NS3 advanced simulator for modeling network performance. Its real world deployment tests are AWS and OpenStack, which deploys NVFs in cloud and monitors to monitor other things. Next. As I said, it is used in AWS for monitoring performances of real world deploying testings. NVF performances. It the high overhead of CPU is not used. The virtualization consuming CPU and memory is low. The interface between VNFs, one VNF can slow down on the others. And the optimized placement that put VNF close to users or resources. It is used in AI and ML to predict traffic, springs, and scale accordingly. Next. There are many challenges in any NVF performances like security issues. Virtual systems cannot be vulnerable. It can be hacked very easily. No standard frameworks. Difficult to compare performances across systems. The multi-vendor complexity means different systems might not work well together. If any one of the VNF is gone or it becomes very slow, then it will slow whole the process and it will not give effective results. Next.
Now, moving forward to the next topic, which is future trends in NFV performance improvement. Integration of 5G technology, which is 5G integration with NFV using network function virtualization, NFV to make 5G technologies more flexible, scalable, and efficient. AI-driven network optimization using artificial intelligence AI to analyze, predict, and improve network function performance automatically. Edge computing and NFV convergence, running NFV services closer to users at the network edge to reduce latency and improve speed. Fully automated orchestration, automating NFV deployment and management to reduce manual work and increase efficiency. Security enhanced NFV solutions, adding stronger security to virtualized network functions to prevent cyber threats and death bridges. Now moving forward to the demonstration of project. First step to set up our project. So we need to install Docker first. So our main goal of the project is to evaluate the network performance of virtualized network functions using Docker. A Docker is a container which is lightweight, portable, and isolated environment that runs applications. It includes various things like running the app, which includes code, system libraries, dependencies, and configurations. Based on these containers, by running and analyzing IPEF3 tests for TCP, TCP reverse, and UDP traffic, and visualizing the results for comparisons. Now, evaluating network performance will measure us how well our VNFs, virtual network functions, handle network traffics. Virtualized network functions, VNFs, use Docker containers to simulate NFV, which is the foundation of next-gen networks. IPEF3 tests for TCP and UDP tests different protocols and directions to simulate real-world conditions, analyzing and visualizing results. The graph helps you and others clearly see differences in the throughput. Here, first we have to install Docker. So we have to write command like sudo apt install docker.io. which will install all the required dependencies for the project. And now we have to start our Docker. So we will write command as sudo systemctl start Docker, which will start the Docker. And the next command is sudo systemctl enable Docker, which automatically starts the Docker when the system is booted. Now, going for the next step, we must create simple virtual network functions to analyze the performance of networks. So let's first create two Ubuntu-based VNFs by the command docker run dit name VNF Ubuntu bash. This will create a container VNF1 in Ubuntu bash and the another container VNF2 bash in Ubuntu. Now, to communicate these containers to each other, we must establish a bridge between them. So let us create a custom Docker bridge network so both containers can communicate with each other. So we'll write command as docker network create hyphen driver bridge nfvnet, which creates a bridge that establishes connection between VNF1 container and VNF2 container. And after establishing the bridge, we must connect our two containers to the bridge so that connection will successfully establish. So we'll write command as docker network connect nfvnet nf1 and docker network connect nfvnet vnf2. So successfully connected to the bridges. Now communication can be established. Step 3 is to install iperf3 inside both containers. Why we should install iperf3 in VNF? Because we are having two containers. So one container will act as a server and one container will act as a client. So to communicate with each other, we need to establish a client and server establishment to communicate and test the connection and analyze its performance. And to install iperf3 in first container, that is VNF1, we must write the command docker execute it VNF1 bash, which will create an interactive terminal session inside the running container named VNF1. Now we can run commands inside that container to install iperf3 tool so that communication can be done. So we had written the command apt install iperf3, which will install the tool. And after successfully installing the tool, we will now exit from this terminal to to back our main terminal. Same for the VNF2. Now step 4 is to get first container's IP address and to host it as server. So we'll write as command docker inspec-app range.network settings.network IP address dot n VNF, which will give us answer as IP address of VNF1, which is 172.19.0.2. Now we will host VNF1 container as a server. So we'll write command as docker execute it VNF1 iperf3-s, which will now hosting as a server. Now in the new terminal, we run our client, that is VNF2, by the command docker execute it VNF2 iperf3-client and the connecting server IP address, that is 172.19.02, which will which will give output like this. So here VNF2 client is connecting to the VNF server at IP of 172.19.0.2 at port number 5201. The output shows us transfer and bitrate. At each second, around 3.7 to 3.9 gigabytes is transformed. The bitrate or speed. Bitrate is defined as the amount of data transferred per second in network connection on and around 32.1 to 33.7 gigabits per second, indicating high throughput. Then the next column we can see that is RETR, which is retransmissions. Retransmissions indicates lost packets. Some peaks, for example, in our case 50, 48, suggests minor congestion or buffering issues. Now, for further analysis and future enhancements, we want to save our output. So we'll write command as docker execute itvnf iperf3-c and the server name and the file name, that is iperf output.txt, which will save our output in the form of txt file. For example, like this, it will show our details. Now, to analyze from the graph, we have used the matplot library in Python and written some code to establish a graph, which will look like this. From the graph, the key observations are x-axis, which shows time in seconds. Y-axis shows bit rates, represents measured network throughput in megabits per second. The bitrate starts around 31,500 megabits per second. There is a gradual increase until around 3 seconds. A sudden spike occurs at around 3 to 4 seconds, reaching its highest bitrate, almost equal to 33,800 megabits per second. After the peak, there is a decline followed by fluctuations in throughput. The bitrate stabilizes around 32,500 to 33,500 megabits per second in the later seconds. So possible variations will be network congestion, variation in available bandwidth, container performance, Docker container CPU or memory limits might cause fluctuations. Hyperv3 building effects. Some packets may be queued using sudden jumps. Reverse traffic impact. If running TCP reverse mode, bidirectional traffic could affect the results. Now to run more tests like UDP, TCP, TCP reverse. What is TCP test? TCP test is transmission control protocol is a connection oriented protocol that ensures reliable data transfer, uses three-way handshake to establish connection. TCP reverse test, a variation of standard TCP test where the direction of traffic is reversed. Instead of the client sending data, the server sends data to client. UDP test, user datagram protocol, is connectionless protocol that does not guarantee delivery, order, or error checking. We have written some script like this, which will automatically generate start the server and gives result in the form of TCP result.txt, TCP reverse result.txt, and UDP result.txt. We have plotted a graph to compare their analysis. So this is the Python code, which will generate a code like this, graph like this. The key observations is TCP in blue line. The bitrate starts around 42,000 megabits per second, increases slightly, then drops efficiently at around 7 seconds. Possible causes of drops will be network congestion, TCP retransmission due to packet loss, CPU bottlenecks in handling traffic, TCP reverse line, that is in orange color. This line is stable around 32,000 megabits per second throughout the test. Reverse mode sends data in opposite direction. And UDP in green line, its bitrate is very low, around 500 megabits per second. Possible bottlenecks and fixes are TCP drop at 7 seconds, low UDP performance, TCP versus TCP reverse difference. So we can conclude that TCP fluctuates, showing congestion or processing issues, need more issues. TCP reverse is more stable, suggesting network is asymmetric. UDP is underutilized, like due to default settings. Conclusion: NFV provides scalability, flexibility, but requires performance evaluation. Optimization techniques like DPDK, AI-based scaling, efficient, enhance NFV performance. Future trends focus on automation, AI-driven decision making, and enhanced security. References: research paper on NFV benchmarking, performance analysis reports from networking vendors. Thank you.